Welcome back. I'm sorry, I forgot to mention that I'm splitting this video up into some smaller videos to make it hopefully a little bit easier for you guys to watch if you're busy or something like that, just to kind of break it up for you. Okay, so the next topic that we're going over on this lecture is going to be radiation. Now, radiation is the transfer of energy by particle waves or photons, packets of energy. There's a couple different terms you can use here. But the main thing to remember about radiation is going to be its most important general characteristics is its wavelength. So if you see here, this is going to be like a crest and another crest. So the distance between these two crests is going to be considered its wavelength. So certain objects emit shorter wavelengths where those crests are closer together, and then some of them have longer wavelengths where those crests are further apart. And that's going to determine the strength of the radiation, all sorts of different properties about it. But radiation does travel through space at the speed of light in a vacuum, which is actually going to be 3 times 10 to the 8th meters per second, or 186,000 miles per second. That is super fast. Okay, so what emits radiation? All objects with a temperature greater than 0 degrees Kelvin, we already talked about this, they emit some type of radiation. So I emit radiation, my computers emit radiation, the desk emits radiation, Argos does, you heard me. Anything around basically that has any type of temperature whatsoever is going to emit some sort of radiation. But there are actually a couple of laws that go along with radiation, and they always hold to be true. So the first one I feel is kind of, I don't know, intuitive. Warmer objects emit more intensely than colder objects. So the sun is warm, so warmer than the earth, so it's going to emit more intense radiation than colder objects, like the earth is colder than the sun. So that law is called the Stefan-Boltzmann law. Now, warmer objects emit at a higher proportion of their energy at short wavelengths than colder objects. So that means that the sun, the distance between those two crests, is going to be shorter than the Earth's radiation that's emitting from it. And that's called Wien's law. Now, we have these examples you can see here of the humans and the sun and the earth. So human, out of those three, are the coldest. So, well, not on average. So I guess the Earth would be the colder one out of the three, and they actually emit a higher proportion at a longer wavelength, and also less intensely. Okay, so here's kind of like an idea of what these wavelengths actually look like and what different types of radiation there is. So something that doesn't emit a lot of radiation, it doesn't very warm or anything like that, has a very long wavelength there, and that's going to be the AM radio waves. And you can go down here to see infrared waves, which are going to be, have a shorter wavelength here. But, remember, we're increasing in energy over here. So as we go down, the energy is going to get stronger. Visible light has even a shorter wavelength, and then down to X-rays, which have very, very, very short wavelengths. Okay, so this is going to be kind of, the solar radiation that we receive and what spectrum and what, where it actually is in the wavelength. So the sunlight's peak radiation intensities per wavelength are in the visible spectrum. Really, our atmosphere and everything around it is absolutely perfect. The sunlight also is perfect as well. It emits almost all of its radiation in the visible light spectrum, which means somewhere between purple and red. Yeah, and overall sunlight is primarily made up of visible light, infrared, and ultraviolet. That's basically what the sun is emitting, mainly in that visible light spectrum. The rest of it's kind of, negligible. Okay, so terrestrial or long wave radiation. Terrestrial is going to be like the Earth, planet Earth here, and, the planets mainly emit infrared radiation. So that's going to be the wavelength that we actually are going to emit. The radiation emitted by planets occurs mainly at wavelengths that are longer, which makes sense because it's colder than the sun. So you can see here that the solar radiation is going to be shortwave, so it's going to have like really a lot of little wiggles as it's coming in. And then the terrestrial radiation that's coming off of the planet is actually going to be more, you know, like a longer, little snaky kind of looking line. Let's see. So just to reiterate, the sun is much hotter, so the solar radiation consists primarily of shorter wavelengths than the planet Earth. You can see down here that the longer radiation is from the Earth here. And this is really mainly coming from the sun. It's mainly in the form of visible light. Okay, obviously the sun provides the Earth with its energy. The question is, how much of the sun's energy does the Earth get? Okay, it depends, because the sun's energy is either scattered or reflected away, absorbed or transmitted. So in different areas of the planet actually do different things in different, let's say, numbers. So what is the scattering, absorption, and transmittance of solar radiation? Scattering happens when solar radiation is reflected. So it's going to come down and it's going to be reflected off. It doesn't have that heating element to it. The things that are going to scatter the sunlight are going to be things like gases, aerosols, clouds, sometimes the Earth's surface. And then absorption, which is going to be that warming effect, occurs by gases and clouds and the Earth's surface. So it just kind of depends on different things. And then transmittance happens when solar radiation passes through the atmosphere to the surface, where it will be absorbed or reflected. It just kind of comes down. So here you can kind of see these wavelengths coming from the sun. You know, this is the incident solar radiation coming in, and it's either going to be reflected, it just reflects off, or refracted. If you guys remember what refraction is, through like water, you know, it's going to kind of go through it and like bend and then come off of there. You can see here that, you know, it's at a shorter wavelength though than the one that's absorbed. The one that's absorbed here is at a longer wavelength. Okay, so absorption of short wave radiation by atmospheric gas molecules is fairly weak. It's not a lot, it's not very strong, and most of it occurs at the Earth's surface. So we actually are heated from the surface, and then it kind of comes up. Instead of, a lot of people think we're heated actually from the sun above, but we're actually, you know, the sunlight comes down and hits the Earth, and it warms the Earth, and then we're warmed actually from below. Most atmospheric gases do not interact strongly with long-wave radiation, meaning it just kind of lets it just directly pass through it and then down to the ground, except for greenhouse gases. So greenhouse gases actually absorb certain wavelengths of the Earth's long-wave radiation. So since it's absorbing it, then it has a warming effect. So that's why these greenhouse gases are generally, you know, we hear about it a lot with climate change, global warming, that kind of idea, because it's going to help warm the planet. Now, here's actually kind of I want to say, some graphs side by side of different greenhouse gases and in what a spectrum, or like where in the radiation, what type of radiation it actually is going to absorb. So you can see here, like for instance, water vapor is going to absorb a lot down here in the infrared spectrum, and so is carbon dioxide. Okay, but like molecular oxygen and ozone is actually going to reflect a lot over here in the UV area. Okay, and then this one actually down here shows us just like the net average of all the gases. So just by these graphs, you can see that nitrous oxide and methane, you know, they're really poor at absorbing. They kind of are over here in this spectrum. Sorry, guys. You do an update, I guess. Okay, but over here, you know, the water vapor and the carbon dioxide is actually going to be a poor absorber of this visible light, but a very good absorber of infrared radiation.